Hello, Assalamualaikum. We will continue the topic in active filter and now we'll move to the low pass filter. Okay, so hopefully at the end of this topic, students should be able to distinguish between the ideal and typical frequency response of low pass filter and the order of the filter. You will look into first order and second order low pass filter. And then you should be able to derive the transfer function for the active low pass filter using inverting and non-inverting op-amp. And then design an active low pass filter using op-amp. And lastly, solve question related to active low pass filter involving op-amp. Okay, first we look into what is a low pass filter. Okay, low pass filter is just a circuit that can pass only signal within the frequency lower than the cutoff frequency. So if you see here, this is FC or high cutoff frequency. You have a gain over here at the pass band, but at the stop band you won't get any gain. This is the ideal frequency response, and actually in real you'll get this type of a frequency response. There is a slope, okay, between the pass band and the stop band. Okay, now we look first into the passive filter. Okay, shown here is just a resistor over here, R and C, and this is a low pass filter circuit. Okay, so any signal lower than the cutoff frequency can appear at the output. If you put something over here, the frequency is less than the cutoff frequency, it will appear at the output. But if the signal over here, the frequency is more than the cutoff frequency, you won't get anything at the output. Okay, but this is a passive first order low pass filter because there is no active element, just passive element R and C. Okay, and the output is taken over the capacitor over here. So you can get using a voltage divider. Your VO is simply VI multiplied with the impedance of the capacitor, VI multiplied with ZC divided by the total impedance in the circuit, which is R plus ZC. Okay, ZC impedance of the capacitor is 1 over J omega C. And if you put ZC over here into the equation, so what you'll get is VO equals to VI multiplied with the ZC just now, 1 over J omega C divided by R over 1 over J omega C. Okay, so if you simplify that equation just now, you'll get a transfer function for the passive low pass filter. I write it over here, it is in omega. Okay, omega domain, frequency domain. V out over V in is 1 over J omega C over R plus 1 over J omega C. Multiply with both upper and lower with J omega C. So you arrive at 1 over 1 plus J omega RC. So this is the transfer function, which is the equation that describes the behavior of the low pass filter circuit just now. So now, from this equation, we substitute omega, okay, with a value of 0. What will happen to this? So if omega is 0, this term will be 0. So you have 1 over 1. So meaning that your transfer function will give you 1, meaning that that is the highest gain for your circuit just now. Okay, and then substitute the frequency omega at a very large value, meaning that at infinity, so 1 divided by 1 plus this term is you multiply with infinity, these terms will get bigger. 1 divided by something, a very large value over here, 1 over infinity, so this term will goes to 0. Okay, so your transfer function give a value of 0. So the maximum you'll get a gain of 1 at a low frequency, but at a very high frequency the gain is 0. So this is showing a low pass filter characteristic. Okay, so at omega 0 just now we get a gain of 1, so this is the maximum at frequency 0, but at a very high frequency, the gain is 0. So what will happen between from the frequency 0 to the infinity? What will happen to the gain? So you will see that the gain, okay, it will retain at 1, but after the cutoff frequency, it will be lower. Okay, it is decreasing at the rate of minus 20 dB per decade. So meaning that a very high frequency, the gain will be reduced. So this is the characteristic, or this is the frequency response of a low pass filter. You have a gain, the maximum is 1 at the pass band or at the frequency less than the cutoff frequency, but the gain will slowly decay. Okay, so this is another view of the frequency response. Just now the maximum gain is 1, so 20 log of 1 is 0 dB. You plot over here 0 dB. At the cutoff frequency over here FC, the gain will be reduced by 3 dB. So at minus 3 dB, this is the cutoff frequency. Okay, so this is the slope just now I mentioned, minus 20 per decade. So between the top until over here, which is 20 dB. So if you plot it correctly, there is a minus 20 dB with a factor of 10. So this is 1 decade. You will be reduced by 20 dB. Okay. So the transfer function just now, H omega is the relationship between V out over V in. We get that the value is 1 divided by 1 plus J omega RC. So this is a passive filter. Okay. From the transfer function, we can find the cutoff frequency. In order to get the cutoff frequency, you just equate this is J, this is called the imaginary part of the equation. This is the real part of the equation. So equate these two. So you get 1 equals to omega RC, just get the magnitude. So find what is the omega from this equation. So that omega is called omega H, which is the high cutoff frequency for low pass filter, and the value is 1 over RC. So meaning that the resistor and capacitor that you use in circuit will determine your cutoff frequency. And for this one, omega, so the unit will be in radian per second. And if you want to find the frequency in hertz, FH is 1 over 2 pi RC. Okay, because omega is 2 pi F. Okay, this is in hertz. And at this cutoff frequency, the value of your reactance is equals to your resistance. Okay, so this is the cutoff frequency. Okay, so when you plot it, okay, so that is your cutoff just now. So you get 0 dB at the pass band, which is 1 in linear scale, and then the slope will be minus 20 dB per decade. And there is a phase shift over here between V out and V in. Over here, your V out and V in is in phase. Yeah, there is no meaning that your VO and V in will be similar in phase. But after the cutoff frequency, at the cutoff, it will be the difference will be minus 45, and after that, at very high frequency, the difference between VO and VI is 90 degrees. There is a phase shift between the input signal and the output signal because we have a capacitor. Okay, please remember that capacitor, the voltage across the capacitor cannot change instantaneously. Similarly, if you use inductor, it is the current through the inductor cannot be changed instantaneously. The circuit just now we have a capacitor, so the reactance of the capacitor XC is 1 over 2 pi FC, so it depends on the frequency, the value of the reactance. At a very high frequency, okay, 1 divided by infinity, this term is 1 divided by a very large value. So meaning that this is an open circuit, okay, the current is 0, but if the frequency is 0, 1 divided by 0, the reactance is very large. Okay, so this is the reactance of the capacitor just now. Okay, so that's why there is a phase shift between VO and V in. All this while, what I have talked is about the passive filter. Now we move on to the active filter. So for active filter, just now we just have RC over here, which is the passive filter. Now you just add on in this for the circuit with another circuit, which is in this term is non-inverting amplifier using op-amp. So the red block is the non-inverting amplifier, and in order to determine the cutoff frequency, you have to find the transfer function. This is now we just look at this. This is just the filter, just similar to the passive filter just now, but instead of calling the output as VO, it is the input to the positive terminal. So V plus equals to V minus. So you can get the equation just similar to the passive just now. V plus will be using voltage divider, V in multiply with the capacitor reactance, divide by R plus the value. Okay, over here simplify the equation. Okay, define V plus over VI, and from there this equation will give you the transfer function just between VI and V plus, and you can get the cutoff frequency similar to that passive filter. So this RC will determine the cutoff frequency. Okay, and for the amplifier, it is a non-inverting amplifier. You have learned in chapter 1 in using op-amp. So just now this is the filter. Now we'll look into the amplifier. So since it is a non-inverting amplifier, the gain will be A is 1 plus RF over R1. The ratio of RF over R1 plus 1 will give you the gain of this circuit. Okay, so if you combine these two, okay, the transistor, the op-amp, the amplifier with the filter over here, you can get the transfer function. So this one you obtain from this part, this one from the amplifier, multiply these two, so that is the overall transfer function. So if you look at this transfer function, the difference with the passive just now, instead of 1, there is a gain A over here. Please remember that for active filter, you can have an amplification. So the frequency is similar. Okay, you still get the minus 20 per dB per decade, because this is determined by the filter circuit. Okay, so the slope or roll off still 20 dB per decade, or it is similar to 6 dB per octave. I have talked about this previously. Okay, and now we move to the non-inverting amplifier to an inverting amplifier. So if you remember in chapter 1, we'll talk about integrator. When we put a capacitor over here, it is an integrator. This integrator will act as a low pass filter. So how do I get the transfer function and the cutoff for this circuit? First, if you look at this capacitor, what is the reactance? The reactance will be 1 over 2 pi Fc. Okay, if F is greater or it is infinity, your reactance will be 0, so the circuit will become a short circuit. If it is a short circuit, you won't get any gain. Your VO will be 0 because it is tied to the ground. Okay, so next, what if the frequency is 0? Okay, your reactance of the capacitor will be in infinity. It is an open circuit, so this circuit is just a inverting amplifier. Remember, VI, you put it into the negative terminal. R2 over R1 will be the gain of this circuit. Okay, so it is a low pass filter, and if you plot, you'll get the maximum gain is minus R2 over R1. This is at the cutoff. The gain is still 20 dB per decade, since it is a first order low pass filter. Okay, now we have known already that the integrator is a low pass filter. Now we want to find the transfer function for this circuit. Okay, so if you look over here, for this particular circuit, using the Kirchhoff current law, we can define the current over here as IR1 going into this particular node, and leaving the node is IRC, which is the current to these two in parallel through R2 and the capacitor over here. So this is the equation just now. This is IR1, which is the current moving from Vi to this particular node, and that particular node is your V minus, and this V minus equals to 0 because it is connected to the ground. So Vi minus 0 divided by the resistor R1 over here is the current IR1, and for these two it is parallel, R2 parallel with ZC, the impedance of the capacitor. So IRC will be flowing from this node to the output node. So it will be V minus, which is 0. So you write it 0 minus the output node, which is VO, divided by those two parallel. These two parallel is simply R2 multiplied with the impedance of the capacitor, which is 1 over j omega c, divided by R2 plus 1 over j omega c. It is just like you finding two resistor in parallel, but in this case it is not resistor, but it is a capacitor. Okay, so simplify this equation. So you'll get that Vi minus 0, so it is simply Vi divided by R1. And for this equation, this thing simplified, you get it is a minus VO over R2 divided by 1 plus j omega c R2. So from this to this, there is several steps actually. So that one is you have to do some mathematical expression, simplify the equation. So finally, you'll get the transfer function AV, which is the relationship between VO over the input over here Vi in omega domain frequency, okay, angular frequency. So VO over Vi will be minus R2 over R1 divided by 1 plus j omega R2C. So if you look here, the gain minus R2 over R1, this is the maximum gain for this particular circuit when the capacitor is open just now. Okay, and from this transfer function, using the denominator over here, you can get the cutoff frequency. Okay, so this is the transfer function just now. If you look over here at omega 0, what will happen to the gain? Okay, this term will be 0 minus R2 over R1 divided by 1. So you simply get minus R2 over R1 at omega 0. And if you put it in the transfer function, omega is infinity. So what you'll get is, this term is infinity, 1 plus infinity is a very large value, minus R2 over R1 divided by a very large value, it will goes to 0. So from 0 to infinity, okay, so what you'll get is the behavior of the low pass filter. At a very low frequency, you get a gain, and at a very high frequency, you didn't get anything. Okay, because after the cutoff, there will be no more gain. Okay, so the transfer function describes the behavior of the circuit. Okay, and then from the transfer function, also we can determine the cutoff frequency. And if you look over here, at the denominator, this is the real part, this is the imaginary part, equate these two. Okay, 1 equals to omega R2C, and from there find what is omega. That omega is your cutoff frequency. Okay, so your omega is 1 over R2C, that is in radian per second, or F is 1 over 2 pi R2C. So this is the cutoff frequency for the integrator that acts as a low pass filter. Okay, so that's it about first order high pass filter. So the next topic will be still a low pass, but a second order low pass filter. Okay, thank you. And don't forget to subscribe to my channel.